for introducing me. So basically, this talk will be focused on non-Fermi liquids. In particular, I'll be focusing on quantum critical points, where okay, yeah. So basically, it is this kind of quantum critical points, and if you go to very low temperatures, you get a high TC superconducting phase, and then if you cross the transition temperature, you get the metallic phase. But this is for some reason that I'll explain are called strange metals. Okay, so to understand strange metals, let us review what we know about normal metals, and this is given by or this can be explained very nicely theoretically with the help of Landau's Fermi liquid theory. So Landau observed that if we take a finite density of electrons, then their properties do not necessarily depend on the details of the microscopic systems that we might choose to study. So broadly, we have two properties. So first, we have the ground state, which is characterized by a sharp Fermi surface in the momentum space. And then on top of the ground state, the low energy excitations come in the form of what we call quasi-particle excitations. So schematically, if we take a three-dimensional isotropic system, then the Fermi surface is like the surface of this sphere. And then if you want to represent it also mathematically, then it's the Fermi surface is actually the jump in the fermion occupation number n of k at 0 temperature. And this definition works both for free and interacting electron systems. So for free system, the jump is exactly equal to 1. Whereas for interactions, the jump is reduced from the value 1 as shown here. And usually we use the letter Z to denote this jump. Okay, so let us try to get some intuition from these pictures that I have drawn. So suppose you take this Fermi surface and then you add an extra electron to the system. So in the first picture, we have a non-interacting system, then we have a Fermi surface, and well, we have just added an extra electron. That's it. But now let us add interactions. Then schematically, what you have to do or what you have to imagine is that because you have added this extra electron, it can create virtual electron hole pairs because it can kick out electron from inside the Fermi surface, take it outside. And then there can be multiple such processes. So it's like a perturbation series, and you have to sum over a series of processes. Now, through this methodology, you can find out the Green's function or the correlator of this system. In particular, if we compute the coherent part of the single particle Green's function of this interacting Fermi liquid system, then we get a form like this, a functional form like this. So this Green's function or the retarded Green's function is a function of these variables, omega, which is the energy measured with respect to the Fermi energy, and the momentum or the momentum vector k. Again, we divide the momentum vector k into two parts. One is perpendicular to the Fermi surface, which we denote by k perp, and we measure k perp with respect to the local Fermi momentum. And then the other part is the tangential part, which we denote by k parallel. So this is what appears here in the Green's function expression. Now, apart from this k and omega, we also have two parameters, z and gamma. So I had already used the symbol z in my previous slide, but I'll talk more about it. So if you look at the form of the denominator of this function, we immediately see that there are this emergence of quasi-particles, which are nothing but the collective low-energy quantum oscillations, because there are these poles of the Green's function. Of course, they are not the delta function poles because there is a finite decay given by this gamma. Okay, so this gamma parameter appearing in the retarded Green's function is actually the decay rate, as I already told you. And if you compute it within using this Landau's Fermi liquid theory, it turns out to be omega square or the energy square. And since we are measuring omega with respect to the Fermi surface, omega is exactly 0 on the Fermi surface. That tells us that the quasi-particle lifetime gamma inverse diverges as we move closer and closer to the Fermi surface. Now, this other parameter, z, is actually the quasi-particle weight, which takes the value between 0 and 1. And physically, it tells us how much overlap there is with the quasi-particle with a free fermion or a free electron. And you can talk about this overlap because it's an assumption of the Landau's Fermi liquid theory that the ground state of the interacting system is adiabatically connected to that of a non-interacting problem. Also, these quasi-particles are in one-to-one correspondence with the non-interacting fermionic system. Again, if we theoretically compute within the Landau's Fermi liquid theory various thermodynamic and transport properties, they turn out to be very much similar to those of free fermions. For example, the specific heat goes as linear in temperature T. The resistivity rho, if you compute for electron-electron interactions, that is proportional to 1 over tau, where 1 over tau is again proportional to T square, if you consider this in a Fermi liquid theory. Lastly, if we compute the imaginary part of the self-energy sigma for this interacting system, that is actually proportional to gamma, and then I told you gamma is proportional to omega square. So all these things we can compute using the simple Landau's Fermi liquid formalism. So what in the beginning we could think that it's a complicated problem because of interactions, but has been reduced to a simpler one thanks to this Fermi liquid framework. Okay, but that's a very nice story that we get to read about in our textbooks, or we can see it in most metallic systems. But we are also aware of systems where these nice features are not quite obeyed. And these I will broadly call non-Fermi liquid metals. They are also sometimes called strange or bad metals because the power law behavior in many physical quantities are not the same as what you would expect in a Fermi liquid. For example, one important property that catches our attention often is that the resistivity goes as linear in T, and it crosses the so-called Mohr-Tierfeld-Regel limit, the Maillard limit, without showing any such saturation. So suppose if you take a normal metal or a Landau Fermi liquid theory substance, then this is how it will behave, like this green line. So it will go, rho will go as T squared, and at some point it will saturate, obeying this Maillard limit. Whereas for the strange metal, it will just go as linear in T and it is not going to saturate. So this kind of strange behavior tells us that the quasi-particles that describe this Landau Fermi liquid theory, they cannot be the emergent degrees of freedom in these non-Fermi liquid metals. Okay, so once more, let us then try to see where we can find this kind of strange behavior, or what kind of systems can host this kind of strange behavior. Now, often we can come up with an effective action for describing the theory that we have at hand, and often it consists of electrons and some emergent bosons or effective bosons, which describes the low energy effective field theory for the system. Now, in many cases, this effective boson turns out to be massive, and in that case, we get this nice picture of long-lived quasi-particles, which gives us back this Fermi liquid picture. But in some cases, the boson can become massless, where these quasi-particles are then driven to destruction, such that we get a non-Fermi liquid system. And one such important example, or where we can find this non-Fermi liquid signatures, are these quantum critical points, which anyway I'm going to focus in this talk. So let us look at this phase diagram where we have temperature along the vertical axis and some tuning parameter along the horizontal axis. And there is some continuous phase transition between some ordered phase and disordered phase, which can be explained with the help of a bosonic order parameter. So this bosonic order parameter becomes massless right at the quantum critical point, and then it can mediate very strong interactions between these fermionic quasi-particles, ultimately leading to their destruction. Now, some examples will involve antiferromagnetic critical point or asymptomatic critical point, which I'll focus on in this talk. There can be CDW or charge density order parameters, gauge fields, which can be actual gauge fields or even artificial gauge fields that can emerge in condensed matter systems. Okay, so in particular, I will focus on something called the critical Fermi states. That means I'll be looking at systems where we have a sharp Fermi surface, but the Landau quasi-particles may get destroyed. That means in the beginning, I showed you this nice Green's function you could write for an interacting Fermi liquid. But for a non-Fermi liquid, it's no longer possible to write this kind of a Green's function. And as I said, this kind of critical Fermi surfaces will be associated with quantum critical points associated with the onset of various kinds of orders or even gauge fields. Okay, so now how come it's possible that we do not have well-defined quasi-particles, but we still have a well-defined Fermi surface? So let us look at the series of diagrams, which was explained by Senthil. So suppose we have we have a situation where this quasi-particle can vanish continuously everywhere on the Fermi surface. So here I have plotted the ground state momentum distribution, and then along the horizontal axis there is this momentum k. Now in the first picture we have a bona fide or well-defined Landau Fermi liquid, but since it is interacting, there is a jump in the particle distribution function, and the jump is less than equal to less than 1 because it's interacting. Now, by looking at where this jump is occurring, you can identify the position of the Fermi surface. That is, there is a well-defined Fermi surface for this problem. Now imagine that we have crossed the phase transition point and we have gone to the phase where the Fermi surface has completely disappeared. So in this case, n of k, or the distribution function, is smooth everywhere. So there is no notion of Fermi surface in the second picture. But now imagine that the first picture is just changing into the second phase. That means this jump has just closed. So in this case, the n of k function is continuous at kf, but its derivative is discontinuous. That means the discontinuity has been replaced by a King singularity. So still there is a singularity. So through this singularity, we can still identify the position of the Fermi surface, or we have a well-defined Fermi surface. But since the z has gone to 0, you no longer have a well-defined Green's function, or you no longer have the well-defined quasi-particles. Okay, so let me try to explain to you this in a pictorial manner. So in this kind of systems, I've told you that we have this fermion boson interacting with each other, and this serves as a perfect recipe to get a non-Fermi liquid at a quantum critical point, for example, because the fermion boson coupling becomes strong, particularly in low dimension, like in 2D, even if we start with the bare value of a coupling, which is small enough. So as we flow to lower and lower energies, the bare coupling will grow stronger and stronger, ultimately driving this quasi-particle weight z to 0 so that the quasi-particles get destroyed completely. So we can imagine about this system like this, that suppose we are taking the Fermi surface far away from the quantum critical point, then it looks like this calm sea with very little fluctuations. But now, suppose we are approaching this quantum critical point, then it looks like this violent and stormy seas, such that it undergoes very violent fluctuations. So basically, the critical fluctuations at the quantum critical point, which originate from the bosons, will couple to the itinerant electrons on the Fermi surface, which again then undergo very violent fluctuations. So our attempt to describe this kind of non-Fermi liquids is to take a sharply defined Fermi surface, which couples with gapless or massless order parameter fluctuations of a boson. And those of you who are familiar with Feynman diagrams, then we can describe this electron-electron scatterings here as being mediated by the propagator of a massless boson. Okay, so now the natural question is that, well, why theoretically even, why should we be interested in this kind of systems? Now, I already showed you this cartoon of this high TC material and strange metal. So the point is that this kind of non-Fermi liquid phases or non-Fermi liquid metals are quite ubiquitous whenever we look at the phase diagram of a high TC material, like here for the cuprex. So here there is this putative quantum critical point marked by this red dot. But of course, in experiments, we mostly don't see this quantum critical point because it is always hidden by a superconducting dome. But if we go above the transition temperature Tc, then we get this strange metal phase whose presence can now be felt, which shows this strange power law behavior, like the resistivity going as linear in T, or the imaginary part of the self-energy going as omega to the power d by 3, where d is the dimensionality of the system. In particular, in 2D, it's omega to the power 2/3, which again tells us that the Landau quasi-particles cannot be the emergent degrees of freedom in this strange metal regime. Now, often we find that the strange metal regime and the superconducting phase are lying at the same doping, for example, in the cuprates. And so understanding the strange metal phase might hold the key to understand this holy grail, that why the TC is so large in this high TC materials. Okay, so as theoreticians, we want to get a controlled approximation of this kind of quantum field theoretic systems where we have these fermionic excitations interacting with some massless bosonic excitations. So fortunately, we were able to find some analytical framework with the help of the tools of quantum field theory, where we used ideas like dimensional regularization and renormalization group theory. And our controlled approximation allowed us to compute various things like critical exponents right at the quantum critical point, and then optical conductivity, which one can measure in experiments. Okay, so now let me try to qualitatively explain to you what we mean by this mathematical tool of dimensional regularization. Suppose we take an isotropic 2D metal so that the Fermi surface is like this red ring, and suppose it is undergoing very violent fluctuations. Then the probability of this black dot of getting hit by this fluctuation is very high when we are at 2D. But now mathematically, let us imagine that we are embedding this ring in a higher dimensional space. For example, here it's a three-dimensional space, and so we have this Fermi line embedded in this 3D momentum space. So by doing this, what we have done is that we have suppressed the quantum fluctuations by adding these extra dimensions perpendicular to the Fermi surface. So you can imagine why it is happening, because you are just reducing the density of states by adding these extra dimensions. So this is basically the philosophy of doing this dimensional regularization. So we artificially add some extra dimensions perpendicular to the Fermi surface, and then our goal is to find something called the upper critical dimension DC, such that if the physical dimension of the system is greater than DC, then it is well described by a mean field-like theory, which is, in this case, it's a Fermi liquid theory. And this is a well-known notion from StatMech and QFT. However, if the physical dimension of the system is less than or equal to DC, then we cannot quite trust the universal scalings that you would extract from a mean field theory. So that's inapplicable in some sense. But now what we can do is that we can carry out a perturbation in this parameter epsilon, which is the difference between DC and the D physical, as long as epsilon is small enough to justify a perturbative treatment. Okay, so with these ideas, we applied it to various different systems, but the simplest system that we considered was the Ising nematic quantum critical point. So what do we mean by that? So suppose we have a square lattice which has a tetragonal symmetry, then via interactions that is spontaneously broken down to rectangular or orthorhombic symmetry. That means if we look at this diagram, so here we have a quantum phase transition as a function of, again, some tuning parameter. So on one side, we have a Fermi surface which has the square-like rotational symmetry. When we go to the other side of the phase transition, the Fermi surface is elongated either in the vertical or in the horizontal direction. So this is what this Ising nematic quantum phase transition involves. And this is brought about by an order parameter phi, which is a real scalar boson, and it becomes massless right at the quantum critical point. And it is argued that this kind of phase transition might be present in some high TC materials like cuprates, ruthenites, and pnictides. Okay, so as I said, we want to describe this quantum phase transition. So there are these bosonic degrees of freedom. So first, let us see what is happening on the bosonic degree of freedom side. So I already told you that here we have the order parameter, which is a real scalar. And the first thing we want to write down is a Landau-Ginzburg-like action for this bosonic order parameter when it undergoes fluctuations. So the free energy, or the Landau-Ginzburg part, turns out to take the same form as an Ising order parameter for magnetization. So this action has the same form as you would write for an Ising order parameter. And that's why that's one reason why we call it the Ising nematic order parameter. Now, if we couple this order parameter to the Fermi surface, what it does is that suppose we have a circular Fermi surface or a spherical Fermi surface, then it is kind of the Pomeranchuk instability of the Fermi surface in the angular momentum 2 channel. So that's why it stretches it either in the horizontal or in the vertical direction, depending on the expectation value of this real scalar bosonic field. So this is then the interaction part where this phi field couples with the fermionic fields which are residing on the Fermi surface, the psi dagger psi like this. Of course, this is the full interaction, but then we are interested in the leading order in momentum interaction, so we'll expand that to get the leading order term. Okay, so now let us see how this entire system is then behaving. So we couple these bosons to gapless fermions, and then it changes the nature of the quantum critical fluctuation. So no longer we can say that now the QCP is in the Ising universality class, because coupling it to the fermions does something non-trivial to the system. But roughly, let's see what we get from a naive random phase approximation, though it's not controlled, but still we can get some idea that how the system should behave. Now, first, let us look at the bosonic degrees of freedom. So if you compute the one loop bosonic self energy, then it takes a form like this. The pi takes a form like this. Now, we know that when we do quantum field theory, the bosonic modes, they look like the quantized harmonic oscillator, right? But when you compute this one loop bosonic self energy, it gains a part like this, and this exactly looks like an overdamped oscillator. And that's why the name comes. We say that this bosonic mode is Landau damped. Okay, next, what happens to the fermionic degrees of freedom? Okay, to start with, we can always start with the quasi-particles, but then what do the bosons do to these quasi-particles? So for that, we have to compute the fermionic self-energy sigma. And if you compute the imaginary power of sigma, which is proportional to this gamma or the decay rate, that turns out to be omega to the power 2/3. So it's not like omega squared that you would get for a normal Fermi liquid. So basically, this is the RPA result, and we formulated a controlled approximation rather than this uncontrolled RPA. Okay, so first let me tell you what were the results that we got. Now we computed this kind of things in generic dimensions. That means we computed it for two-dimensional systems as well as three-dimensional systems. So for the 2D Ising nematic quantum critical point, the Fermi surface is one-dimensional, and I will denote by M the dimensionality of the Fermi surface. So M equal to 1 Fermi surface is the thing to consider here. Now here we find that the fluctuations are effectively local in momentum space. And that means the various Fermi surface patches are decoupled from each other. They don't talk to each other. And this is in the momentum space, remember. Okay, so using this fixed point theory or this control theory, which I will explain in more technical details later, we computed the optical conductivity, sigma, as a function of the frequency of an applied AC electric field, and that we found to go as omega to the power minus 2/3. And this is close to some experimental values, which was reported in, and these experiments were performed on some optimally doped cuprates. Okay, so now let us see what happens for a 3D system. Now, what do we mean by this Ising nematic transition in a 3D system? It actually means the same rotational symmetry breaking in the XY plane, but now embedded in a higher dimensional space. That means here it's embedded in a 3D space. Now here we have a 3D system, and so the Fermi surface has dimensionality m equal to 2. And here we found that the fluctuations are non-local in momentum space. That means all the Fermi surface patches are entangled with each other. As a result, although we were interested in looking only at the infrared physics, there is some non-trivial mixing of the ultraviolet physics with the infrared physics. And the ultraviolet physics is, it has an energy range of the order of kF. Now, although they are all entangled fluctuations, this turned out to be less violent, and this turned out to be a marginal Fermi liquid rather than compared to the case of the n equal to 1 Fermi surface. And we also show a peculiar thing that because of this non-trivial mixing of UV and IR physics, the two loops and the higher loop corrections are vanishing in the system. Okay, now there is a combined feature we found both in 2D and 3D cases. Now, I already told you in some of the beginning diagrams that we don't see a naked quantum critical point because it is always almost hidden by a superconducting dome. So the next thing to compute was naturally to see how does the competition between the non-Fermi liquid phase and the possible pairing stability pan out at 0 temperature. And my computations show that the superconductivity wins, which explains that why this quantum critical point is always hidden by a superconducting dome. Okay, so there are some other examples from my work. For example, one can consider this organic superconductors where there is a transition as a function of the applied electric field, where first you have a homogeneous superconductor, then you have an FFLO superconductor, and then you have a normal metal phase, and it's possible to get a quantum critical point or non-Fermi liquid behavior in this region. And then, okay, this has not been realized experimentally because I have heard that it's very hard to get like very good disordered free or pure samples. But suppose one can do it, then this system has the potential of showing us the naked or unmasked QCP because there might not be any competing orders which will hide this quantum critical point. Okay, so here are some other examples from my work where I considered Fermi surface now interacting with the transverse gauge field, which turned out to be very much similar to the isognommatic case, but the vertex is a bit different, so the calculations are a little bit different, but the aim scalings, etc., are very much similar. And then also I considered situations where I have hot spots rather than the entire Fermi surface becoming hot. Okay, so now let me try to give you some technical details of whatever I tried to explain in words. So for that, we need to first try to set up a coordinate system, but let us see that how this fermionic and bosonic degrees of freedom, first of all, interact. Now, as I said, we are interested in looking at the low energy limit or in the IR limit, where the fermions on the Fermi surface must mostly scatter tangentially. Okay, so and we assume that there is an inversion symmetry. So suppose we are considering a fermion at this point of the Fermi surface, then we should also consider its left moving counterpart here. So how much time? I'm already over time. Okay, so I will try to rush and probably we can discuss later. So here the slides tell us that for a one-dimensional Fermi surface, the points are completely decoupled, which I told you in the momentum space, whereas for a higher dimensional Fermi surface, it's not. So then that's why this UV-IR mixing comes into the picture. So since I don't have much time, I will just tell you the coordinate system that we need to use. So we have to erect a coordinate system where we take a patch of the Fermi surface where we have this tangential momentum vector and the perpendicular momentum vector. And with that, I take this right moving and the left moving fermions on the two antipodal points and write down the fermionic part of the action, the bosonic part of the action, and the interaction between the two. So anyway, there is a trick of writing these two plus and minus fermions in this Dirac fermion-like form just to facilitate the computations. And then we add some extra special dimensions to do this dimensional regularization. Finally, by using this RG idea and computing this one loop self-energy diagrams, we have to first compute the DC for this system. And the DC turned out to be m plus 3 by m plus 1. And that also helps us define an effective coupling constant, which is actually perturbatively controlled using this E and the Kf, which are the coupling constant and the Fermi momentum. And finally, with this E effective, we have to find out the beta function. And the fixed points are given by the zeros of the beta function. And there is a Gaussian fixed point and an interacting fixed point. And we will be focusing on the interacting fixed point, which is actually the stable fixed point in the theory because the RG flows are towards this fixed point. Okay, so this is how this RG is done. And since I'm out of time, I think I'll just skip it, skip everything, and maybe we can discuss in the break. Okay. Sorry. Thank you for your attention.
Okay, there's time for a couple of questions. Yeah, Bala.
So I do not really understand how you get those modes in the case of the DC.
Oh, I think that was just a way of speaking. It's just an analogy that this is kind of the Goldstone modes as you get for a boson. But Okay, I think you should take the terminology with a pinch of salt. I just meant that whatever bosons you had in the theory, it's not, maybe that terminology should not be used.
Okay,
Just one small remark. This results conductivity, singular conductivity proportional to 1/(ω)2 that you cited in one of your slides. Was reconsidered in the last few years by several groups, including people working around supersession. And it turns out that this result doesn't hold. For circular Fermi surface and for any convex Fermi surface, instead you get
Okay, so yeah, I had this conversation with Maslov because he actually brought this point. But okay, there are issues. I don't think it doesn't hold is as a blanket statement is true. So there are various issues in that in our computation when you should be careful in computing whatever you have found for this convex things. So I think you're referring to this Maslov's recent computation also where they
number of groups. They all
yeah. So that is one paper I know of. So, but I don't think that's the statement that can be made because there are several things like what you assume or what you are actually computing. For example, we extrapolated it like we are doing it for d equal to 2, right? But then our DC is 5/2. Then the coefficients, we are just putting it DC equal to 2 and computing the coefficient, right? It may not be correct because we're extrapolating from 3/2 to 2. So it's possible that the entire coefficient in front is going to vanish. So yeah, there is various things. Yeah. I mean, we can discuss it. I'm aware of this point and we had some conversations regarding it.